Welcome to this explainer. Today, we're decoding the invisible safety systems running our modern infrastructure. We rely on vast transportation networks every single day, but we rarely stop to think about the digital brains keeping everything moving safely. We're going to dive right into the incredible architecture behind modern computer-based interlockings and how engineers design for safe output. So, how exactly do you build a computer that is literally never allowed to fail? It's a huge question, because unlike old-school mechanical levers or traditional relay systems, computers introduce terrifying new ways to break down. With hardwired physical machines, failure modes are pretty predictable. But the second we hand control of 1,000-ton high-speed vehicles over to software and microprocessors, we're dealing with a whole new level of complexity. How do you trust your life to a machine that can crash, freeze, or just glitch out? Well, here's our core problem. Microprocessors are inherently complex. Their failure modes are wildly unpredictable compared to traditional hardwired logic. If a physical relay interlocking fails, we almost always know why. But microprocessors? They have millions of transistors running thousands of lines of embedded code. Out of the box, they just aren't designed to meet the extreme, zero margin for error safety requirements needed for something like railway signaling. So here's our roadmap for today. We'll start with the microprocessor problem, move into 2 out of 2 architecture, upgrade to 2 out of 3, and finish up with the power of diversity. Let's get into it. First step, the microprocessor problem itself. In a high-stakes environment like railway interlocking, a single memory overflow or a tiny voltage spike could trigger a catastrophe. Remember, an interlocking system is essentially the strict traffic cop of the tracks. Its one job is to prevent conflicting movements. If the internal logic glitches, it might accidentally give a green light to 2 trains on intersecting paths. That is the absolute worst-case scenario, and engineers have to prevent it at all costs. The reality is, engineers have to assume hardware and software failures will absolutely happen. It's not a matter of if, but when. Think about the threats. A nearby power line causing electrical noise, a momentary voltage dip corrupting a mass calculation, or a hidden software flaw, like a stack overflow. The golden rule of safety engineering isn't pretending these won't happen. It's designing a system that remains safe even when they do. That brings us to our first line of defense, the 2 out of 2 architecture. Take a look at this incredibly strict voting mechanism. You've got 2 completely separate processing channels, A and B, executing the exact same route request. Instead of letting one computer make all the decisions, both are fed identical inputs. They run the exact same calculations, and then they compare their answers. It's exactly like having 2 independent accountants verify the same spreadsheet. If their numbers don't match, nobody gets paid. If channel A and channel B disagree, this system acts like a brutal bouncer. It immediately shuts everything down to enforce a safe state. We call this the fail-safe principle. In rail networks, failing safely means stopping all movement. If processor A says the track is clear and B says there's a train ahead, the system doesn't guess. It throws its hands up, cuts the power, and turns all signals red. But there's an issue with that, which brings us to the 2 out of 3 architecture. See, 2 out of 2 has a massive vulnerability. If it shuts down every single time a minor glitch happens, the whole transport network grinds to a halt. It's a classic engineering trade-off. We have to balance ultimate safety with system uptime. A safe railway is fantastic, but if trains can never run because a single computer had a tiny voltage spike, the whole system is practically useless. We need reliability just as much as safety. So we upgrade to a 2 out of 3 setup. By adding a third processor, the system can actually vote on a command. If channel A glitches and spits out a dangerous output, but channels B and C produce the correct, safe output, the voting mechanism spots the anomaly right away. It safely ignores the crazy processor, executes the action agreed upon by the majority, and alerts maintenance. The trains keep moving and safety is never, ever compromised. Finally, let's talk about the power of diversity. Okay, we've solved random hardware failures, but we still have a terrifying blind spot in our voting committee. What if all 3 computers make the exact same mistake? If they're all running identical software, a single systematic programming bug could cause all 3 to confidently agree on an unsafe action. It's a safety engineer's worst nightmare. Think about it. If 3 identical calculators have the same programming flaw, they'll all give you the same wrong answer. Our voting system would see 3 matching votes and blindly execute a dangerous command. This is what's known as a common cause failure. It's a single flaw, usually a software bug, that hits all identical processors at exactly the same time, completely bypassing our clever voting protections. They're essentially just echoing each other's hidden flaws. The fix? Diversity. By forcing the channels to use completely different hardware and software, engineers practically eliminate the chance of a simultaneous bug. It is absolutely brilliant. If channel A uses a processor from company X and channel B uses an entirely different architecture from company Y, and they're programmed by separate teams using different languages, the odds of them generating the exact same bug at the exact same millisecond are practically zero. This layered diversity is the real reason we can trust computer-based interlockings. To wrap up this explainer, let's look at the ultimate trade-offs between safety, uptime, and cost. A single processor? Sure, it's cheap, but it's completely unsafe. A 2 out of 2 setup guarantees safety by shutting down, but your system uptime takes a huge hit. And then there's 2 out of 3. This is the gold standard. It outvotes the errors to give you high safety and high uptime. Though, yeah, it definitely comes with a much higher hardware cost. So next time you board a train, ask yourself, how many computers are voting on your safety right now? I hope this explainer completely changes how you look at the invisible architectures protecting our daily commutes. Behind the scenes, diverse processors are constantly checking, double-checking, and voting to guarantee every movement is flawlessly safe. Thanks for hanging out with me for this deep dive, and keep questioning the hidden logic of the world around you.